This is going to be the third part, and hopefully the last part of this lectures on quantum thermodynamics. And today we're going to revisit the concept of quantum engines and also quantum batteries in this context. Engines, either in its classical or quantum version, they are simply physical systems that exchange energy from thermal baths, right? And they convert it to work, right? You want to extract some kind of energy to supply their machines. And in a quantum context, these baths can be thermal or not. That's not something we're going to cover today, but in the classical thermodynamics there was thermal baths. Now in quantum we can use other kind of resources, like purely quantum resources, information resources, some optical resources like squeezing, for example. We can use all of them to convert this kind of energy into work, useful work. Another characteristic, or the main characteristic, when we're dealing with quantum engines is the fact that the working medium is going to be a quantum system, right? We can think of this quantum system to be the simplest one, like a spin and magnetic field. We can create some kind of thermodynamical cycle to extract work. Depending on the system we're dealing with, this work will be, the amount of work extracted in a cycle will be higher or lower, and also the power. So for instance, quantum systems like spins, harmonic oscillators, cavities, we can imagine a working medium to be whatever you want, really. So those are the main characteristics when dealing with quantum engines. And we began these lectures, the first lecture in fact, with an example of the first implementation, right? The first implementation of a quantum engine, which dates back to 1959 by Scoville and Dubois, and it was a 3-level maser, if you remember it. We have basically a 3-level system. If you attach this one to a thermal bath at a given temperature, another thermal bath to these 2 levels at another temperature so that TH is larger than TC, you can create a thermodynamical cycle maintaining this population immersion, right? And you obtain an efficiency. Let's say efficiency of 3-level maser it was always less than equal to Carnot's efficiency, so it can operate as a quantum engine. So it was the first implementation. Basically, let's say that the foundational problem of this area of research in physics, of quantum thermodynamics, is, it started with the implementation of a purely quantum engine. Something that operates between 2 thermal baths and you can extract some kind of work, some kind of energy from them. In order to study the dynamics, let's consider, as we've been doing throughout all the lectures, the Lindblad equation, right? Which will give us the temporal evolution of our density matrix of the state of the system through time, right? Integrating that, we can obtain what's the state of our system at a given time, t. So these are the ideas, the main tools, and now we are going to explain how we can. So if we consider a classical engine, basically I mean an actual engine, like a car engine, right? Different strokes that perform different kind of temporal evolution, different kind of processes, and when we attach all of them, we can close the cycle and extract some work in this manner we presented before. So in the quantum regime, there are, let's say, two great kind of engines. First of all, have these sort of strokes. I'm going to focus on the quantum counterpart of the purely classical engines, which are the engines composed of, as I said, several strokes, right? You can imagine, for example, a 4-stroke engine, like a diesel engine, auto engine, Carnot engine. All of them are 4-stroke engines. So you have 4 different kind of processes, and when you attach them together, you can extract energy from them. So if we consider these sort of engines, basically we can define some kind of dynamical, some kind of map for the whole cycle, which is basically the product of the number of strokes we're considering. Right? If we have 4 strokes, there will be 4. And it's customary usually to put here some kind of projective operator. So basically, if you have an energy through time diagram, we know that at the end of the cycle, the variation of energy is 0, right? If it's a thermodynamical cycle, if it's an engine. So mine is the shape of our energy through time. And we're dividing in strokes. Let's say this is 1 stroke, another. So the thing is, it's customary to define this kind of projector operators in order to measure the energy at those points, right? So I have my first stroke, let the system evolve, I measure time. We do it with this kind of projectors. Do the same for the second stroke, I measure energy here. The same for the third stroke, and finally the same for the fourth stroke. Right? This is the case, for example, for a 4-stroke engine. There are some studies where they compared the fact of measuring after each stroke or measuring at the end of the stroke. I can provide you with some references.
Or measuring continuously.
Or measuring continuously, exactly. There is a paper coming to mind by some, I think it's PRX Quantum, and it's probably 2021. I'm not sure about that. They compare these two kind of measurement scheme. So, as I said, this is the map for the stroke, and the pk is the projector of measurement operator for at the end of each stroke. Okay, let's find out what's the shape of this operator. So this lambda k, this map is going to act on our state of our system, right? On our rho. So this lambda k is basically given by the Lindbladian, right? This equation, the Lindblad equation, can be written, as we all know, as some kind of super operator, right? The Lindbladian. So this lambda k in general can be expressed like the exponential basically of the Lindbladian we have in this stroke. So this, at the end of a stroke, we have right? this lambda k acting on our system, we integrate it, and we obtain a temporal evolution of the system along this stroke. So, and this is for k from 1 to n, since we have n strokes on the cycle. This map, this sort of evolution is general for a given limblarian. We can have also, as a special case of this particular case, unitary evolutions. If our system is evolving adiabatically, the system is closed. So we don't have this part. We only have the unitary evolution. So this lambda k becomes an unitary operator, which is basically the exponential of the Hamiltonian, basically, right? Okay, this is the case I said for the case of unitary operators. So now we have this lambda k, the shape of the lambda k. Let's figure out what's the shape of the pk. That's a projective operator, since we are measuring energy at the end of the strokes. We want to build this pk to be a projection on the eigenbasis of the Hamiltonian at a given time t, tk in this case. So the way to build that is basically at the end of each you can write down your Hamiltonian as, say, this way, right? In its eigenbasis, so that this projective measurement on that basis would be simply nothing there, right? So
this is the identity then. You're essentially just doing the identity.
In this eigenbasis.
In this, yes.
Right?
But this pk is the identity.
Yeah, basically in that basis, let's say.
Sorry, no. But what is k?
K is the time. At time t, at the end of the. Basically, you diagonalize. You have your Hamiltonian in a diagonal basis.
Yes.
These eigenvalues, eigenvectors can change in time. In fact, if it's a derivative of time.
This pk is
the identity.
Yes. But the thing is, now, so you have your system. Your state evolves in time. You get to the end of the stroke using this evolution. So to figure out what's the next step here, you have to measure, right? Let's go t plus to the instant of time right after the measurement, right? This part, for example, and this is gonna be yeah, like that.
No, there is something that we are missing. It's identity.
This is the identity.
If it is the identity, that's
Yeah, but the thing is this row k plus 1 can have non-diagonal terms in this.
No, then we cannot be the identity, because the identity does nothing. So this pk cannot be the identity. But why is not the identity?
No, the thing is this can be expanded, for example, in a sum of j, some kind of say.
Okay, so you're inserting the identity as a way to just say that I'm writing the state rho k at t plus 1 in the basis
Yes.
of the state before
Yes.
the measurement.
I want to start a new cycle with a diagonal. In this case, diagonal in that eigenbasis.
But Álvaro is saying what you are saying are different things. think a little bit.
No, but then it cannot be like this.
It's not
Imagine you have that basis, right? Your system is reading that basis, and you just project.
Yeah, okay, but the question is the projector you wrote there
Yes.
is the identity. All of it.
Yeah, it's the identity, yeah.
Okay, but then it's the identity, you're not removing coherences, you're doing the identity. So I don't understand, there's something missing.
there's something missing. Yeah, I think.
If you,
Okay.
say prime, so you have
So this is not diagonal.
you have something, a sum, with some terms, right? And now
No, but it's not the same index I, it has to be a different index j in the K.
what do you want me to write? J. You want me to write J?
Heat on the top. Has coherences now between I and I prime. Right?
Yeah, but in the eigenbasis of the Hamiltonian, it's gonna be diagonal. Because this is a number, this is gonna be another number, so you have this thing and this thing.
Yes,
With a delta I prime.
no, I don't understand why this is. This means that this J basis is the same basis as lambda R. So what's the point of doing the measurement?
What's the point of doing the measurement? So you want the state at the end, you want to measure the energy of our system, of your system, right?
To measure the energy, okay. So the projectors there, I think, they're
Yes.
not the sum over I.
Then the sum over what?
There's something. So you want to make a measurement, to measure the energy, you have to make a projective measurement in the eigenvectors of the Hamiltonian at K.
Yeah.
Okay. So then this PK doesn't have the sum over R, right? It's just this measurement. And then if you do it like that, then this makes sense because then what you do
Then no, there is a subterfuge there. It's not that pk is the sum.
It's
You
without the
have to
sum.
define pki, for example, pki, and remove the summation.
Oh.
Okay, so it's a projector on the eigenspace.
And then you sum on the other. And
This makes sense.
yeah, in there, you have
Um,
to sum over I. No, up. Yeah.
What do you mean?
Here it would be the sum over I of pki
Yes.
from sum over j of pk j.
Yes.
And this
Yeah.
is not the identity.
Yeah.
And then this is what gives you the coherence.
Okay.
Yes.
So if you add the summation there, you get the identity, and then identity row identity is just row.
So
Yes.
there's an easy way to see this is essentially this is what they call the decoherent map. I give you a density matrix and you kill all the off diagonals, right? That's
Yeah, to
essentially-
measure the energy,
Yeah,
Mhm.
exactly.
which is what we're interested in at the of the
Okay.
cycle.
No, this is what you were saying, but
Just
if
that
you
you
put
do
the
the
summation
Yeah.
before,
Yeah.
then you are, because if you put the summation before, then you are adding sum of I of pi row pi, and then
Yeah, it's-
what gives you the
Okay.
Okay. Yeah, that's from my note.
But the idea is that if you want to express the state after the measurement,
There should be diagonal in the
the state of the So now we know how to measure the energy. So how can we measure now work and heat, which is what we're interested in? So if we remember the other lectures, we can write down this. Assume that our cycle, our stroke has time tau. So in general, this is going to be the trace. These two quantities, right? And there are two contributions here. One of them is related to the change of our Hamiltonian, and the other one is related to the change of our system. These two quantities have been considering in these other lectures are customarily defined as work and heat, right? It's important to remark that it's well known that these two quantities do not represent heat and work in several cases, but let's stick with this point. In my opinion, what they lack really is interpretation. Depending on the cycle you have, these two quantities to define the energy change, for sure, it's simply the product rule of the derivative. The thing is, this W, this term doesn't represent the entire W, and this term doesn't represent the entire Q. So the work and heat, flows from the system to your environment, to the baths or the work you're extracting. It's not really given by those quantities. As I say, it depends on the sort of cycles you're considering and the sort of system you're considering. So let's provide you with some examples of quantum engines. The more common sort of engines you deal with in literature are the four-stroke engines. I mean, they are the usual ones. And the simplest case is the Otto engine. You may wonder why, but the Otto engine, as I said, has 4 strokes. So 1, 2, 3, and 4. So the first stroke performed in the Otto engine is an adiabatic compression. Since it's adiabatic, the entire transformation of energy is going to be equal to work, right? The second stroke, it's basically an isochoric heating, where the entire variation of energy can be characterized as heat. Then you have here another adiabatic where the variation of energy is equal to work. And finally, some kind of isochoric cooling, where the entire variation of energy is equal to heat. Right? Basically, compress, heat, expand, and cool. Basically, doing a cyclic way, and you have the auto engine. Note that I'm using the classic, right? Depending on the source system you have, this compression, expansion, isochoric terms will mean differently. So, one of the simple systems you can use to build an auto engine is a harmonic oscillator. Imagine you have a system given by this Hamiltonian. Right? With a time-dependent frequency. And that's dependence of the creation and annihilation operators. So what we're going to do is we're going to build an auto engine with this kind of systems, with a harmonic oscillator.
Sorry, it's not difficult. Just not to confuse, but I say this is not, and then I wrote the same thing. This way. Yes. As I wrote it, it was still identity. Okay. No, because it's just making the sandwich with the eigenvalues of I, so you remove the coherence. The other way around, it was still the identity in both cases. Okay. So then you are projecting into the Hamiltonian eigenbasis.
Now I'm realizing that this is in fact not wrong.
This is what?
It's not wrong. Basically, if I do this,
Yes, that's the correct one.
Exactly.
This is the correct one.
Yeah, with only one index.
yeah.
If you sum over two indexes,
Now,
it's identity, and then you mix, and then you keep the coherence. But if you sum over one index, every time you have a coherence in row, it is
Yeah.
killed by one of the two projections.
it wasn't that bad. So it's just an index.
Yeah, it's okay. You might have it.
Okay, let's.
Nobody important detail, I can confuse you.
Okay, this is going to be our working medium for our engine, and we are going to suppose that at the initial state we have the frequency. Let's call it omega A, right? So at the initial state, the Hamiltonian will be given by h bar omega A, and then a dagger A plus 1/2. Right? So the system, we're going to compress it. First of all, if we compress it, let's make a sketch of the cycle. This first stroke, compressing in this context with the harmonic oscillator is basically closing the spectrum is basically closing this the parabola, right? So that will mean that we will move from omega A to omega B, which is less than equal to omega A. In fact, if it's equal, you do nothing, so it's less than omega A. Sorry, larger than omega A. Yeah, larger than omega A. Then the 2 to 3 stroke is an isochoric heating from 2 to 3. Isochoric in this context will mean that we are not varying the frequency, but we are changing the temperature. So the initial temperature of our system is the temperature we have. So we finish with the cooling. So the temperature is going to be the temperature of the cold bath. So we are moving from some temperature Tc to a colder one, a hotter one. Then we have another stroke, which is the adiabatic expansion, going from omega B, omega A. We are like, if they imagine this as a harmonic track, we are opening the track, and this omega is smaller than omega B, and finally we are closing the cycle by cooling the system, right? Moving from temperature hot to Tc, which is smaller than h. Okay? That's a sketch, the translation of this schematic cycle to the actual system we are having, the cycle. The last thing we need to know is the initial state we are going to consider. Since we want to measure the energy, we need the Hamiltonian, which we have it, and we need the state. So the initial state, since this is a closed cycle, imagine we do several cycles of this. When we get to one, the state is going to be a thermal state at the temperature of the cool bath, right? So say that omega at the omega A is going to be a thermal state represented by tau at a frequency omega A, and temperature, we said temperature of the cold bath. This is given by this kind of expression, right? So basically I give a state whose inverse temperature is the inverse temperature of Tc, and the Hamiltonian is the Hamiltonian we have at A. Right? This is it. This state will vary on time since we are varying h in time. Z is the partition function, which is simply the trace of what you have in the numerator part. Okay. From now on, I will consider the constants equal to 1, and we can compute the energy, the average energy we have at the point A. It's basically a trace of rho A HA, right? And this is given by omega A, the average number of excitations, and the constant. This n, which is harmonic oscillator, it's given by the Bose-Einstein distribution. So you can write this down. If you plug here the Bose-Einstein distribution, you can write this down in terms of the hyperbolic cotangent. Okay, that's the energy at the point A for a given frequency, omega A, and a given temperature, Tc. If you deal with these kind of systems in general, all these hyperbolic functions will appear, basically because you have sums and stuff related to positive exponentials. I mean, real exponentials, sorry. Okay, we have many of them, and they will appear. It's something in a similar fashion happens in statistical mechanics, right? Okay, so now we can analyze the energy changes in the whole cycle. So the first cycle, the first stroke, we have a change in our Hamiltonian from Hamiltonian with omega equal to omega A to another one with omega equal to omega B. You can compute the energy change, which is equal to work in this case. And it's given by this expression. I'm going to use these criteria of taking into account the system. So for work and for heat, if work is done on the system, it's going to be negative. If it's done by the system, it's going to be positive. If heat is absorbed by the system, it's going to be positive. And if it's released, it's going to be negative. The proper criteria, not the other way around. So as you can see, this is negative. That means that we are doing some work on the system, right? It's quite visual if you consider this a trap, and you're compressing the trap, you're basically pushing it. That's why one of the good things about this kind of criteria, it's focused on the system. Then we have hot isochoric heating, So the H remains constant. It's going to be constant at HB, the frequency B. And the temperature is going to change from Tc to Th. This will mean that we have a heat contribution. And this will be equal to the difference of these two terms, right? Since it's a heating process, your system is absorbing energy. If you compute this, it's gonna be positive, as everything should be, right? The next stroke is basically an expansion adiabatically, so it's the analogous one to this case. You can compute the work, this process. In a similar fashion. In fact, the shape is going to be totally equivalent, right? The shape. So we have some difference in the frequencies and then the cotangent of the frequency over the temperature of the system. This part is going to be larger, equal than 0, since omega b is larger than omega a. And the hyperbolic cotangents are a positive function in the positive, right, shape of the something like that. And finally, the last stroke, it's gonna be a cooling, the final one. So we have the heat contribution that is left to close the cycle. Okay, and this for sure, you can compute it. It's negative, since the system is releasing energy, releasing heat. How do we check that our thermodynamical cycle is correct? We basically compute the duration of the energy along the cycle. If you sum all terms, you get this equal to 0. So since it's an engine, one of the parameters we are interested in is the performance of the cycle, which is basically the total work over the heat absorbed, right? You can use the fact that the energy variation on the cycle is 0, so this can be computed as 1 plus QC with QH here. And if you do so, if you just divide this expression by this one, you get basically this term. I think something mistake there. That is a mistake. Right, this term is equal to this term. They cancel out, and you have the quotient of the frequencies, right? Okay. That's the performance of our engines. if we use the relation now between heats, right? You divide one over the other. You can realize that this quotient we have here, it's going to be larger or equal than the quotient of the temperatures. That will mean larger minus equal. Is correct?
I think it's inverted.
Inverted, right? This one? Yeah, this makes sense. So, sure, the performance of the Otto cycle is less than equal than the one of the Carnot cycle. Okay? So you can see this is a pretty nice example for a really simple engine with a simple working medium, which is only a harmonic oscillator, and we can compute everything related to thermodynamical quantities. There is, I would say, well, it's kind of a problem, the fact that the entropy, the von Neumann entropy, it's not clear if it entirely characterizes the actual entropy, the actual thermodynamic entropy of the system. So usually this kind of entropic analysis, like we do in classical thermodynamics, they are not performed here. They only remaining work heat. So there are some studies dealing with the entropy, but it's not the usual thing. This engine has a problem, a huge problem. When you build an engine, what you want to do is to extract power. The problem is we have two adiabatic strokes here. In an ideal way, they would take infinite time to perform. That means that the power is going to be zero. So you need some kind of a trade-off between the performance you are doing with your cycle, you're having with your cycle, and the power you are extracting from the cycle. That is given by another figure of merit in engines. So it's what's the efficiency you can extract from you can have from your engine if you extract the maximum power available. That is called the so it's confusing there. Kurzon-Arbon efficiency, and it's basically defined by 1 minus Tc over Th. That's the efficiency at maximum power. If you compromise a bit of efficiency, you can have the maximum power output from your engine. It's gonna be less than 1. We have there less than Carnot's. You can show that if you maximize the power output, which is basically the sum of these two terms, you can reach with this kind of engines, maximizing the power output, you can obtain this bound. Well, okay, the Kurzon-Arbon efficiency. Experimentally, what you try to do is basically optimize these two strokes. You don't let the system evolve adiabatically for long times. You do it at some point you think it's proper to move on to the next cycle, to the next step in the cycle, and that's it. You don't take infinite time to perform the expansion equally for the cooling and heating. You don't let the system thermalize for infinite.
Can I ask here about this? So one idea is what you say. Is that you say, okay, I don't wait an infinite amount of time. Now it's sufficient enough, and I do it. The other thing is to do it with a quench, right?
Yeah.
So how does this affect it? If I quench the system to take it faster, let's say, I know. No, one way is okay. I quench.
At this point, I would have to analyze it.
Okay. And the
I
other
think
there's this notion of these shortcuts to adiabaticity. Are these used?
experimentally, you mean?
Yeah, I don't know, or theoretically.
You usually see prepare, if I'm saying this correct, you can prepare your system to have a different state, let's say, with some similar properties to the state you have in these points, in order to evolve faster
Yes.
to the stationary state, right? That is a shortcut for additivity.
Yeah.
And they are done by unitary operations, right? Usually.
But I don't know if there are papers with shortcuts to the additivity and heat engines.
And heat engines, there are with processes, I mean single processes, but for a whole engine,
But there should be some.
they should be.
But usually these shortcuts to additivity or they are more popular in quantum computing, in adiabatic quantum computing.
No.
That is slightly different problem that you have a Hamiltonian and you change it very slowly and you want to remain in that state or maybe in state.
Yeah, this is my question. I know that people use it in adiabatic quantum computation, but I don't know if they have been used in this context.
Here there is a difference because you have it's not that you are changing adiabatic expansion, yes. The same in the sense that you are expanding a Hamiltonian, you are changing a Hamiltonian very slowly. The one drawback is that you have a very mixed state. And I don't know, in adiabatic quantum computing, they usually work more on purity.
Yeah.
No, because there is also these acceleration processes that were proposed by Igor Lesanovsky and Antonio. But we didn't apply to this because they are prepared only for pure states.
Mhm.
These are thermal states. So I don't know if there is a simple way of mapping from one case to the other.
Yeah. Okay, this is a simple case of strike engine, of auto engine. There are more samples, as I mentioned before, and the one with the spins. And here we do have a model, a more realistic model of a quantum piston, or quantum piston engine, let's say. Basically, you have a cavity of a given length, and you have a two-level system inside. So if you let these two radiate, this photon, let's say, they would push the engine, the piston, and move back and forth. The thing is, this model is, we studied it, and it's providing us with really nice results. Basically, the fact you have a cavity and a two-level system inside, it's well studied in quantum optics. It's called the model is called the James Cummings model, and basically the Hamiltonian has three terms. One of them taking into account the atom, another one taking into account the cavity, right, and some kind of interaction term between the atom and the cavity. And this one, like, right? We studied this, and we also proposed a new interpretation for quantum work based on the analogous case, in the case of the expansion work, averaging some kind of radiation pressure operator over time, right? It's basically the electric field, the quantized electric field related to these particles, plug it here, and you get the same result as the one we saw before, right?
You got the same.
Up to
For this case.
for this case.
And we prove it analytically, it's not just somewhere.
It's proven analytically in, well, this omega t, it's basically a multiple of omega ct, right? And if you want to remain this kind of this infinitum approximation, the rotating of approximation, if you want to remain this regime, this term, this case should be small, really small. And we prove this to be I think it was k squared. So it's small, square is even smaller.
So you want the interaction essentially to be very small.
Yeah, to remain within this regime. Okay, that's related to engines. Basically, you can model any kind of engine you want, defining properly the strokes, defining properly the system you want to model, you want to use. You can use it. You just need to take into account the fact that at the end of a cycle the energy should be zero, the energy variation. What I mentioned about the entropy, it's not quite clear that fundamental entropy represents truly the thermodynamic entropy of the system. And yeah, any kind of time-dependent Hamiltonian, you can imagine if you attach your system, if you define as a properly your system, you define properly your strokes, you have a decently defined Hamiltonian, and you have two thermal baths, you can build an engine. Either if it's a feasible one or an interesting one, that's with the results, but a priori you can define it. So this one of the main applications in quantum thermodynamics, basically it's the natural extension. And now let's move on to batteries. The concept of battery in quantum thermodynamics is basically the same one as the classical counterpart. It's basically you have a system, right? Let's simplify it with two levels basically. And you want to store energy and release it. Okay, so one kind of work to use it to supply the kind of machine or the kind of system you want. So let's define a battery, a more general scenario. Quantum battery, it's called AQB. It's a d-dimensional system with non-degenerate energy levels from which energy can be extracted or possible via unitary operation. Okay, so you have your energy levels. If you want to move from one to another in both ways, you can do it via unitary operations. Okay, that's basically a battery. In math terms, this Hamiltonian, the Hamiltonian representing the battery, will be given as a d-level system in this way, in the Hamiltonian eigenbasis for the energy. The values of energy must be increasing, and since it's not degenerated, there are no repeat values for the energy. Okay, that's basically the definition of battery. Any kind of quantum system you can imagine that verifies this can be considered as a battery. The simplest case, it's a two-level system in the presence of a magnetic field. Right? You can define two states of energy epsilon and minus epsilon, right? I'm going to call this state the charge state, and this one is the discharge state. And Basically, in order to extract the energy, you can construct a Hamiltonian depending on time, which will be equal to the Hamiltonian of your system. In this case, this H0 or this one with two others, plus some kind of potential depending on time, which will act on the time you are extracting the energy from the system, right? If you extracting energy, say, from T0, this Vt will be defined this interval, right? Since we are extracting energy via unitary operations, the work extracted from your system will be the trace of rho H0 minus trace of rho at a given time tau that's the difference of the energies. How can we determine this rho tau? Since we said it's a, let's consider closed systems, which is the simplest case. Since it's closed, the evolution will be unitary, right? So you have some kind of unitary operator we're going to define now. Is O0, right? The initial time. This u for given time t is going to be given by the exponential of minus I over h bar. This is acting from t0 to tau, right? Since it's a unitary stroke. Okay? That's the work, that's the amount of energy we can extract from the battery. What we're intending to do is to extract the maximum amount of energy from the battery. That's what we wish. How can we do it? Basically, let's define that maximum work extracted from the battery, considering this is the general definition for the work, and I'm going to cover all the possible use. And all those use, I'm going to choose the one that minimizes this amount. I'm subtracting this, I'm going to cover all of them, right? Number of u that's the maximum amount of work I can extract from the battery. This is called ergotropy. The maximum amount of work, of energy in general, that I can extract from a quantum system is called ergotropy. And it's obtained by minimizing over all the use possible, the one that minimizes this amount. Okay? As you may imagine, covering all the possible use, it's almost impossible. There may be infinite operators U to move from one state to another. So let's define a state sigma so that so I'm going to define a state sigma so that I can extract more energy from it. So there are the states. No matter the amount of the kind of operation I do on the system, I can extract more energy from it. These states are called passive states. right? If we represent these states in the diagonal basis of the Hamiltonian, are defined or can be defined this way, right? Diagonal in this basis, so that the energy, this kind of eigenvalue graph here, will be will be decreasing with I, right? As long as I'm moving on the energy eigenbasis, I'm finding states with less and less and less amount of energy. Okay, so those are the states that verify this condition. So the idea is from all these U's I can consider, I want to arrive to a state from which I can extract more energy. So I want to end this trip, let's say, this unitary trip, in a state I can extract more energy. So from that state I can extract nothing more. That means that I can express the ergotropy as this difference. Okay, consider state, consider its passive state, and the path that I'm following from this state to the other one is the one that it's giving me the largest amount of work I can extract from the system. For reasons of time, I'm not gonna show this, but it turns out that this sigma state, these passive states, one can show that all thermal states are passive. So you cannot extract energy from the thermal states. No. You want to build a path, imagine from a given state rho, and to finish at a thermal state. That's the way to do it. With thermal states, I mean these kind of states. Okay. There is some sort of intuition behind this. Let's see if it's clear. When I think of this kind of statements, I imagine how's the distribution of the levels in the thermal states. If you plot, for example, consider one of the simplest cases, the harmonic oscillator. In the harmonic oscillator, the thermal states are described in this way. Right? If you plot, let's call the average number of occupation of your system given by the Bose-Einstein distribution. Let's call it this Pn. Sorry, Pi. If you plot this Pi over I for a fixed n, the distribution has this shape. All of it, no matter the kind of, right? It's always decreasing with I. And that's basically the kind of states we have here. They are decreasing with I, right? So it's kind of similar. And we can imagine this as this kind of states. The energy decreases as long as you are increasing the index. Okay? So all thermal states are passive. That would mean that this maximum work are it's going to be bounded in this way. Okay. Note that all thermal states are passive, but not all passive states are thermal. In the only system you can consider the other part of the equality, so the passive states are thermal, it's in the two-level systems. On the two-level system you have only two levels, so it's easy to verify that all thermal states are passive and all passive states are thermal. Okay? So basically, you want to find a protocol. I'm finishing, sorry. You want to find a protocol to move from a given state to a thermal state at a given temperature. For reasons of time, as I said, there are if you have multiple copies of your battery, you want to consider these kind of states, and in fact the thermal states are verified that are positive for all the copies of your battery, considered as unit cells, right? If you have several batteries in a row, classical batteries, you consider them all of them as unit cells, and you can define a general passive state for the whole system. The only state that verifies that it's passive for the whole one are thermal states. So that's the reason why apart from this, important. So that's basically all. You cannot define the charge and discharge protocols considering quantum if they are not. And also the efficiency in changing the batteries depend on if you are doing it collectively, so you consider the whole system and you charging as a whole, or if you change cell by cell. You can find all this information on the quantum thermodynamic. So in the references I provide you with, the quantum thermodynamic book, the chapter 8, the big book, the one edited by Campaioli, Binder and these people. So the chapter 8 is focused on batteries, so you can find all the information there. Basically, if you do the charge of your collective system, it's gonna be there's gonna be an advantage with respect to doing it cell by cell, right, unit by unit. So that's basically all. With this, I would like to conclude the lectures. Thank you so much for coming, and I hope you have enjoyed it. So thanks.
Maybe a short time for questions. Very
Oh.
short.
I have a very short one. I mean, just a curiosity, what's the problem of the generated energy levels in the case of batteries? I mean, probably a very naive question, but I don't get the idea why do we have to work with non-degenerate energy levels, just for simplicity?
Well, first of all, yeah, it can be for simplicity, but also consider classical battery. Your phone, for example. What if you find a protocol to move? You have the same energy levels. So how can you define a protocol to move to this level or from this level? How to extract energy if it's generated? It's going to be more difficult. Probably it's feasible. I don't know, but probably it's going to be more difficult to define all those quantities if they are degenerated, right? The fact of being non-degenerated makes you, so the picture you have in your mind, if they are defined this way, it makes you very. So I'm consuming energy, I'm descending on the ladder, and as I'm descending on the ladder, I'm descending on the Hamiltonian is well defined by that, right? You can put energy one step above. Probably you can define with degenerated levels, but I think everything is going to be more complicated. Especially not this, but all the calculations you want to do. Okay. More questions if you have? Yeah.
If you have a system of battery of energetic cells, you said that the only possible passive state is a thermal one.
Yeah.
But if you are in other cases, like for example one battery, how do you know that your passive state is in fact thermal, a thermal one?
You can verify that it's a thermal bath easily by comparing to a thermal bath, but you can define a temperature. So in this case, temperature is not like it's given by a thermal bath, which is imposing you a temperature. It's a parameter you can play with. In fact, in this derivation here, if you move from here to here, I didn't have time to explain it. You choose this beta so that the entropy, von Neumann entropy, matches to the one you had before in order to do some inequalities. So playing with the parameter of the thermal bath, you can define that. That's first of all. And second of all, to know if you're in a thermal bath, well, you can do several tricks. First of all, compare it to another thermal bath, the fidelity, for example, some kind of measurement. Or, second of all, you can define, there's a property with the dissipators, right? In general, if the dissipator is applied to a thermal bath, temperature is going to be equal to 0. That's one way to do it. Okay. Dissipator, I mean, in the Limblad equation, the term taking into account the interaction with the environment. All this is for closed batteries. You can also define open batteries interacting with the environment.
I think it's important to say that, just like Álvaro said, this is one definition.
Yeah.
The definition, this is how it works. You can find works where they define it differently, or you can find works where they don't demand that the final state of the battery is stationary. They just say it's sound state. It's not the rule that says this is the law.
Yeah.
Okay? This is the problem.
It's a more usual definition of battery because of its simplicity, mainly. All the concepts, for example, if you read this reference, if you read the chapter of the book, everything is constructed, very straightforwardly. Let's say, I have a battery. This is my definition. So I want to extract energy. How can I extract energy in this way? How can I extract the maximum of our energy? Now, I want to extract the maximum amount. How can I define the states? So, okay, I have the passive states. So what if I consider an array of multiple unit cells? What's the passive state? You get to the definition, and then you get to charge. So it's constructively built, if you want to consider in this way.
One should also say there are additional interesting problems, particularly for batteries, which has to do with, for example, okay, how can I charge my battery the quickest way possible? So for a given energy constraint, charge the battery as fast as possible.
Exactly.
Or discharge the battery.
That's something I didn't have time to explain. But you cannot charge your battery as fast as you can, as fast as you want. And the main reason is this one. It's a sensitivity principle, energy time sensitivity principle. It's called quantum speed limit. That depends on the distance of the states, so the initial state and the final state, and the variation of energy, basically. Exactly. There is another one used in metrology with.
No, this is a subtle point.
Yeah.
And this becomes even more subtle if you are considering open system batteries, because then the speed will change.
Yeah.
But yeah, there are a lot of fascinating problems around batteries in particular. There's also the connection, if you go to the open system framework, there's also these people that are trying to tackle the problem completely from quantum information point of view. They view all this as they do a mapping of, okay, extracting work is the same as doing this kind of information protocol, so let's compute these information quantities and let's relate them and let's see how they relate to batteries and so on. So this idea that Álvaro said that whether or not to charge it cell by cell or maybe charge it globally has to do with communication and the local operations and classical communication, separate operations. So they connect entanglement to all these things, and the field gets richer and richer and richer and richer.
Yeah, the field is huge in batteries, and if ever saw paper by the same guys I mentioned before, this Song guy, he has a paper where he uses an auto engine to fuel a battery, and they connect the whole the two concepts. That's interesting.
Okay, I think we should
yeah.
we should end it here. Thanks, Álvaro.